Hello, my name is John Timperley. I'm a consultant in Exeter, England, and I would like to make a short presentation of how to plan for a total hip replacement stepwise using Mako 4.0. These are the attributes that the robot can add to a cemented hip replacement, or indeed an uncemented hip replacement in many instances. Patient-specific 3D planning, the ability to position a socket with a center of rotation and precise position in the orientation that you wish, femoral offset and depth insertion, combined version where you include the offset of the acetabulum and the femur. You can look at functional orientation of implants. With the software, you can now identify impingement preoperatively. It's good for planning complex cases and in some cases revisions. And I find it incredibly useful to facilitate limited release approaches. The one I use is the SPAIRE technique, which saves Piriformis and obturator Internus, and the only tendon that is released is obturator Externus, and this is repaired with the capsule afterwards. This tendon-sparing procedure is very much facilitated using the robot, which I now use in practically all cases. So how do you plan for it? If you look at socket planning, there are some parameters that need to be optimized. These are the component size, the depth of the medial, anterior, and posterior walls, the surface area of the bone that is to be removed, and the face of the cup in relation to the bony anatomy. And in order to optimize those parameters, you can change socket size, you can move the center of rotation in all directions, or you can change the orientation. And the idea is that you revisit the things that you can change to optimize the parameters that you want to get right. So as a demonstration, here is a case where we're going to carry out the left hip replacement. You can see that it's 2 millimeters shorter, but the combined offset is equal on the right and on the left. So first of all, your Mako product specialist will size the cup to start with. And so this one has been measured to a 52, and you'll start with the size that has been measured either from the femoral head or from the outside diameter of the socket. It's been put at 40 degrees of inclination and 20 degrees of version, which is a sort of average that surgeons use. We can change that later. And for the purposes of this demonstration, the center of rotation of the socket, which is in green, has been put precisely over the center of rotation of the anatomical head, which is in purple. So you can see that there is no movement of that. And you can see immediately that the cup is not deep enough, that no bone is being taken from the anterior wall, and the face of the cup will be protuberant. So we need to change the center of rotation. We're not going to change the size because we think that's right. But if we look at how to change the center of rotation, we've now moved it 5 millimeters medially. You do that by clicking the buttons at the top of the screen. If you do this and then look at the walls, we're going to optimize the walls. If you remember, you can scroll down in the sagittal plane and you can scroll down in the transverse plane to make sure that you're not removing too much bone, and you're keeping a decent thickness of anterior and posterior walls. So walls is one thing. The next thing to look at is the area of bone that's been removed, and this is shown by the green within the screen. And if you now look at the posterior wall and the anterior wall, the size of the cup looks to be correct for this specimen of bone. But if you look superiorly, you can see very little bone is being taken superiorly with the cup with the center of rotation in this position. If we look at the face of the cup, in terms of the version and inclination, it's quite nicely tucked in, very little of the anterior wall of the cup showing proud to the acetabulum. So now we'll go through a further iteration because it's not quite right. So we'll look at those 3 things that we can change again. Well, we're not going to change the socket size because we're quite happy with that, but we are going to look at the center of rotation to try and take more bone to get better grip of the cup. And so what we've done now is move the cup 2 millimeters superior in addition to the 5 medial. And if we look at the walls and scroll up again in the sagittal plane and in the transverse plane, you will see that we're not taking too much bone and that the amount that we're taking is appropriate. And now if we look at the area of bone that's being removed, you can see that that superior part that we were worried that we weren't taking any bone, we are now removing bone from that area and will get better grip of the cup. If we look at the face, you can see if anything, it's even better tucked in anteriorly. And so that looks appropriate for this specimen. It's usually, you can see some of the cup when you look from the back, and you can rotate the bony specimen within the software. You will also, of course, note where osteophyte needs removing. And that is what the cup will finally look like. What about the femoral side? Well, the parameters to be optimized here have the acronym VOLS. We want to optimize the femoral version, the offset. We'll look at combined offset, and we'll take a note of the native femoral offset. We want to get the leg length to the length that we want to achieve, and we want to get an appropriate stem size. But unlike uncemented systems, the stem size is really irrelevant with a system such as the Externus system. So to get those parameters optimized, we will choose the version of that we want to insert the stem. We will choose the offset that is appropriate to achieve the combined offset that we want. We'll then work out how far down we need to put the implant to get the leg lengths correct. And finally, we'll choose the stem size that is appropriate to the internal dimensions of the femur and the body habitus of the patient. And then we'll revisit those to optimize all of those parameters that we wish to optimize. It's worth noting that with a cemented taper slip stem, version, offset, the depth of insertion, and stem size are all independently variable, which is a huge advantage when you're coming to recreate the biomechanics for the patient. So how does this work? Well, an implant has been put in here. We'll first of all choose the version we want. So the native version of this femur, measured by the software, was 4 degrees. We're going to put in what is more traditional of 15 degrees of stem version. We're going to plan for that. And for the purposes of this demonstration, we're starting with a 37.5 millimeter offset stem. Now, the offset has been defined. The leg length is merely how far into the femur you insert that stem. So we've pushed it down to an area where we've got the leg lengths correct compared with the other side. That's where we want the leg lengths to be. If we look at that, then the software tells us that we have decreased the combined offset by 6 millimeters. So this is not appropriate for this patient. We need to do some modification. So what we will do, what we could do is use the same offset stem, put a +4 head on. Of course, if you put a +4 head on the neck, you'll increase both offset and leg length. So you'll need to push the stem in a little bit more. You can plan to do this. So we will plan to get the hip length correct. And you can see that the combined offset is still reduced compared with what you might like to plan. So what you can do next is go to the next offset of stem, the 44 millimeter offset. We're going to go back to using a 0 head and push it to the appropriate position to get the leg lengths correct. You will notice that there's been no change in version. We're still planning for 15 degrees of stem version. With a stem in that position, you can see that the combined offset is now just about perfect. And so that is the stem and the offset. That is the stem that we will plan to put down there. And we will measure from the tip of the trochanter to the shoulder of the implant, how far to insert that stem to get all of these parameters correct. And then that is what the final planned film looks like and is most often achieved at the time of surgery with Mako robotic assistance. So as I mentioned, I use this device, Mako robotic assistance, in almost every case. And the love affair I have with it is augmented by carrying out logical stepwise planning of where I wish to put the implants to recreate the biomechanics for the patient. Thank you for your attention.